All right, welcome to your first lab video for Physics 3A. The first 2 weeks here, you're going to be doing a very simple, silly little lab where you measure the density of water in your kitchen. But it's really, the purpose of it is to get an introduction to error analysis, just very basic tools for analyzing the propagation of error in a calculation where you've done some measurements. So let's consider something as straightforward as measuring the diameter of a soccer ball. Let's say you've got a ruler here, a metric ruler, and hopefully we all know that 1 centimeter, that's 100th of a meter, just like a century is 100 years. And I think we can easily estimate the diameter of the soccer ball to the nearest centimeter. So if you didn't have your face real close to the ruler, if you were looking from a couple feet away, or as it appears in this picture here, you can tell that the diameter of this soccer ball is closer to 22 centimeters than it is to 21, and it's certainly closer to 22 than it is to 23. So if you just had to go with an integer, you're going to pick 22. Now, you may be able to tell that it's a little bit less than 22, but to the nearest ones digit, we would just say 22 centimeters. If I zoom in a little bit here, we could tell that it's not quite 22. We might even be able to judge what the diameter is to the nearest 10th of a centimeter. So if you were to zoom in, you would see that there are 10 divisions within each centimeter. Hopefully, you also know that 1/10 of a centimeter is a millimeter, right? Centimeter is 100th of a meter. Millimeter is 1,000th. And we know that 1,000th is 1/10 of 100th. I'm going to use the letter L to refer to the diameter of the ball here. And I think a reasonable statement would be to say that the true value, supposing there is some number that exists in the universe that most accurately describes the diameter of this ball, and you're trying to get at what that number is, most likely, in all likelihood, that whatever that true value is, it lies within half a centimeter of 22 centimeters. So this statement, this is a way of writing succinctly that you're not sure exactly what the diameter of the ball is, because you can't know exactly with a ruler. You would need a more precise measuring device than just that. But you're very confident that the true value lies somewhere within 21.5 centimeters and 22.5 centimeters. In other words, 22 plus or minus half a centimeter. Hopefully you agree with that statement when you look at the picture here. Notice the way I've written this. I've been careful to include units next to both numbers. This is my best estimate for the diameter of the ball, and this is my approximate estimate of the possible error in that measurement. So I'm going to use the word error and uncertainty interchangeably. I think in a lot of contexts, they're supposed to mean the same thing. So you could say that this measurement is uncertain by as much as half a centimeter, or it could be in error by half a centimeter. Same thing in this context, whichever word you prefer. Now, how did I get that 1/2 centimeter? Well, I don't think it's 22 plus or minus 1 centimeter, because it's very clearly not 21 centimeters, and it's not as high as 23. You might make the case that even this is too large, that you should be able to look at this picture and accurately judge the diameter of the ball to the nearest maybe even millimeter, or at least 2 millimeters, which would be 0.2 centimeters, not 0.5. So I've been rather liberal here in my choice of absolute uncertainty. So one of the first important points to remember here is that this quantity, the estimated, emphasis on estimated, the estimated absolute uncertainty, it's approximate. Don't sweat too much about which number you should pick. Should you go with 0.5 or 0.2 because you could conceivably judge the diameter to the nearest 2 millimeters? It really doesn't matter. 0.2, 0.5, those are close enough. They're the same order of magnitude. You wouldn't want to go with 1 centimeter, and obviously 10 centimeters would be ridiculous. We can do better than saying that it's somewhere between 10 centimeters and 30 centimeters in diameter. That's a silly choice of absolute uncertainty. So when you hear the term absolute uncertainty or absolute error, you should note that there are always units attached to that number. And the units are the same as the units of the quantity that you're measuring. So absolute uncertainty has units. Here's another way of writing it. If you don't feel like writing centimeters twice, enclose the best estimate and the uncertainty in parentheses and then put the units on the outside. That's a little easier to look at. Now, symbolically, here's the notation that I'm going to be using. I won't always put this subscript best, but this makes it nice and clear. The first number is the likeliest value that you would go with, and then plus or minus delta L. This is the Greek lowercase letter delta, and that means absolute uncertainty or absolute error. Always keep in mind this quantity. If you just see a delta X, delta L, delta whatever the letter is, excuse me, that quantity has units attached to it, and the units are the same as the thing that you're measuring. So get very used to this. We're not going to do a great number of labs this semester because of distance learning, but just about every lab that you do, you will be making statements like this. You're telling the reader, who's ever reading your lab report, you're telling them the range of probable values of the quantity that you're talking about. So in this case, my delta L is 0.5 centimeter. Again, absolute uncertainty or absolute error. Here's a third way of stating that result that might be even clearer to some people. It's really a matter of taste, which of these you prefer. On any lab report, I would accept either one. This has the advantage of telling you explicitly what the lower likely bound is and what the upper likely bound is for your measurement. Now, in math, this means something really precise, right? In math, this is telling you that there's no chance that L is equal to the number 23 because that would be outside this range. That's not really true in this context, though. And our treatment here is very topical. We're not going to go into the statistics that behind it all. That's something I would have to review anyway. But I do know that all of these formulas that we'll be using have a firm footing in statistical methods, which can be derived from calculus. What this is really saying is that most likely the thing that you're measuring, if you've done a good job of estimating the uncertainty, most likely the thing that you're measuring lies within this range. Is it possible that it's a little bit outside this range? Yes. There's a chance that the thing you were measuring could be 22.7, which technically lies outside this range, but it's not that far outside the range. And if you wrote down 22, but it really was 22.7, how could you account for that? Well, maybe you were a little sloppy with your measurement. Maybe you didn't place the left side of the ruler flush with the left side of the ball, or maybe your dominant eye is your right eye, and for whatever reason you're squinting your right eye shut and using your left eye to make the measurement, so you've got parallax coming in. There could be small sources of systematic error, they call it, that could have thrown off your measurement. Okay, so if we zoom in a little bit here, now we're able to make a better judgment of the actual diameter of this ball. I think it's pretty clear. Well, this is 21, this is 22, so this would have to be 21.5, right? See how this notch is a little bit longer than all these short ones? So if this is 21.5, we've got 6, 7. It looks like the red line is just after 21.8. It's close to 21.8. So with this magnified view here, we can make a better measurement of the diameter of the ball. And because we've got better resolution, so to speak, we should be able to justify a smaller absolute uncertainty. Previously, I went with 0.5 centimeter. Well, 0.5 centimeter would take you this far on either side of the line. And we're clearly able to judge better than that. So you might even say that the absolute uncertainty is really only as large as 1 millimeter. So I'm writing down 21.8. Maybe it's actually closer to 21.9, in which case that would be an appropriate value for the absolute uncertainty. And the only reason we were able to do that is because I'm using PowerPoint here and we can just zoom in. But maybe if you had a magnifying glass in real life, you could make the same justification. So now my absolute uncertainty is smaller. Just a reminder here, 1 centimeter is 10 millimeters. So if that's the case, we could re-express this result in millimeters, not centimeters. Multiply each of these numbers by 10 to get the same expression in millimeters. Now this sounds like a big number, right? Is a soccer ball really 218? Well, that's 218 millimeters. Remember, 1 meter, I'm not in the classroom to hold out my hands at a separation of 1 meter, but 1 meter is a little over 3 feet. That's 1,000 millimeters. So this is still less than a foot here, 218 millimeters. These are equally valid. Again, it's a matter of taste. Some people might prefer this statement because it doesn't have decimal points in it. So that might make it easier to look at for some people. At the same time, it's a bigger number, which might be more difficult to conceptualize. So either one, as long as it's as long as it communicates effectively. Like if you didn't put units here, we wouldn't know what you were talking about. In this case, my absolute uncertainty here is now 1 millimeter. That's 1/10 of a centimeter. Now let's look at how large that absolute uncertainty is compared to the thing that we're measuring. So this is for my original measurement. If my measurement of the diameter of the soccer ball could be off by as much as 1/2 a centimeter, well, how bad is that, so to speak, compared to 22 centimeters? So we take a ratio, just punch that into the calculator, and I round to 0.022. Well, growing up, you heard this referred to as a decimal. Maybe you weren't aware that decimal is short for decimal fraction. This is just a succinct way of writing a fraction with some power of 10 in the denominator. So I could rewrite this as 2.2 hundredths, right? You might also be thinking 22 thousandths. That's the same thing. So the measurement is possibly in error by as much as 2.2 per 100. Could be off by 2 hundredths, basically. Well, 2.2 per 100 is another way of saying 2.2 per cent. That kind of blew my mind years back when, because when I was a kid, I'd never been told that percent is just another way of saying per 100. Hopefully this is review for most of you. So you could express this ratio as a decimal fraction, or you could express it as a percentage, which is appropriate, whichever makes more sense to you, or whichever seems more convenient. My subsequent measurement of the diameter of the ball was more precise, shall we say, because I had a smaller absolute uncertainty for the same measurement. Now, oops, I've got a typo here. Let me fix that. This says centimeters. That should say millimeters. The second measurement was more precise, 1 millimeter compared to 218. If we express that as a decimal fraction, we get this. And you probably know that the way to convert a decimal fraction into a percentage is just to multiply by 100, which I've done here. So 0.45%. Now that's a little more awkward than a number like 2%. 0.45%, anybody hearing that at least knows, well, that's less than 1%. But it might be clearer actually to express that as 4.5 per 1,000. Isn't this 4.5 in the thousandths place? So rather than saying 0.4 per 100, which is what this percentage is, you could just say 4 per 1,000. I think 4 per 1,000 is a little easier to conceptualize than the percentage. So a percent ratio is not always easier to understand than just a decimal fraction. There's a name for this quantity that we're talking about. Anytime you compare your uncertainty in a measurement to the size of the measurement yourself, you're talking about what's called relative uncertainty. So the numerator here, delta L, that's the absolute uncertainty. If you compare it to, meaning divide by the thing you're measuring, you've now converted that absolute uncertainty into a relative uncertainty. And I'm familiar with 3 different names for that quantity. Usually, I'm just going to call it that. It's a relative uncertainty because you're looking at the absolute uncertainty relative to the thing that you're measuring. But it's also known as percent uncertainty. If you happen to express it as a percentage, then it's just percent uncertainty. It still means relative uncertainty, but specifically with 100 in the denominator. You could also just call it the precision. This term is a little confusing because if I go back a couple slides here, obviously the second measurement where I zoomed in and looked at the diameter of the nearest millimeter, that measurement was more precise. And yet this quantity, which you could call precision, is lower. So if the number representing your precision, if that number is smaller, that actually means a more precise measurement. So I will tend to go with the term relative uncertainty rather than precision. But be aware that that's another way of expressing this quantity. I mean, of course, if you said a precision of 0.4% versus a precision of 2%, I think we all know that the 0.4% precision is more precise, even though the number is lower. So one thing you absolutely have to take away from this semester, and you have to understand before you submit your lab reports, is the difference between these two quantities. A lot of people struggle with this, but hey, now you've got a video. I'm going to do some examples. Make sure you understand the difference. Absolute uncertainty has units associated with, like centimeters or millimeters. Relative uncertainty is dimensionless, because check it out. You're taking a number in centimeters and dividing by another number in centimeters. The units cancel, so to speak. And a percentage, anyway, that doesn't have units, right? You would never say 5% meters. That doesn't make any sense. You're always dividing by two quantities that have the same dimension. Okay, so now that we've introduced the concept of absolute uncertainty and precision, is it fair to say that measuring the diameter of something to the nearest half a centimeter is precise? Is that a precise measurement? Well, you may be inclined to say no, because we just looked at two possible measurements of this ball. One, involving a ruler where you can see the individual millimeter markings, is significantly more precise than the other. So if we're going to compare this measurement to the second measurement, I would say this measurement is not particularly precise. So is it fair to say in general that measuring a distance to the nearest half centimeter is not a very precise measurement? Well, doesn't that depend on what you're measuring? For instance, what if instead of the diameter of a soccer ball, you were to measure the distance between planet Earth and the moon? And believe it or not, this is to scale. I made sure to pull up a picture that was to scale. So the moon is something like 1/4 the diameter of the Earth, and it's way out there, surprisingly. It looks pretty big in the sky sometimes, but it's very far away. Let's now use the letter L to represent the distance from the center of the Earth to the center of the moon. And that number is not fixed. It's changing because the moon's moving in an elliptical orbit, not a circle. And I pulled this off Wikipedia, mean semi-major axis. That's basically like the radius of the moon's orbit. So this is an average value, but that's pretty darn far, right? 384,000 kilometers. That's what, over 200,000 miles away. So I'm going to use that number in a moment. Let's call that our best estimate for the average distance between the Earth and the moon. And if you're wondering how on Earth, no pun intended, how the heck did they measure that, or do they measure that? You can read about it on the web if you'd like. But in the late 1960s, the astronauts allegedly, right, when they allegedly landed on the moon, why is the flag flapping if there's no wind? What's up with that? Why would it be flapping if there's no atmosphere? They put an array of corner reflectors. You can't really tell from this picture, but this is an array of they're like little boxes of mirrors. If you have a box made out of mirrors, then any light coming in and striking that set of boxes of mirrors will just come right back out at the same direction. So it's not going to come in and bounce off in a different direction. It'll bounce right back. And that means if you hit it with a laser beam from the Earth, it should just come right back. So this picture, of course, is totally misleading. That kind of defeats the purpose. I think they added this in Photoshop or whatever. But that's just showing you that there are laboratories in Earth where they actually do shoot giant laser beams at the moon. And they wait for how long it takes the beam to bounce back. I think it's something like 2 seconds, because despite how far away it is, light travels really fast, and we know that speed very accurately. So all you have to do is time the round trip time, or determine the round trip time, multiply that by the speed of light, and you know how far the moon is. I think you'd have to divide by 2 in there. Okay, so they're constantly monitoring the distance to the moon, and surprisingly, they know that distance to like the nearest centimeter or the nearest half centimeter. So half a centimeter may not have been very precise when we were talking about the diameter of a soccer ball, but when it comes to the distance from the Earth to the moon, that's an incredibly precise measurement. Here's another little blurb from Wikipedia. Equivalent in accuracy, they probably meant precision. Equivalent in precision to determine the distance between LA and New York to within 1/4 of a millimeter. Okay. Well, let's compare the relative uncertainties here. So I'll look at delta L compared to L for each of these measurements. And in each case, I went with an absolute uncertainty of 0.5 centimeters. I couldn't determine exactly what the absolute uncertainty is from the Wikipedia article, but I gather that it's on the order of 1 centimeter. So half a centimeter compared to 22 centimeters, it's not particularly precise. If you tell somebody that you know the diameter of a soccer ball to the nearest 2%, they could probably do better than that if they whipped out a ruler. But half a centimeter compared to the number I quoted previously, 384,000 kilometers, excuse me, it's a fantastically small number. So if you want to call this number the precision, you would say the precision is fantastically small. Yeah, that's misleading, right? Let's just say the relative uncertainty is fantastically small. So it's a fantastically precise measurement. I won't be using the word fantastically on a lab report, of course. Now, you could leave it like that. This communicates the relative uncertainty very well. But if I were to move this decimal place over, so I went with 13 instead of 1.3, that's like multiplying by 10, is it not? So if I move this decimal place over, which amounts to multiplying by 10, I would have to pay for it by dividing by 10, and that means moving this power of 10 one integer lower. So I could write that as 13 times 10 to the negative 12th, and 10 to the negative 12th is 1 over a trillion, or in other words, trillionths. So you could also say that scientists are able to measure the distance to the moon with a precision of 13 parts, just round it to 10 parts per trillion, which is easier, I think, to understand than looking at this number. They both work, but 13 parts per trillion, if you happen to know that a trillion is 1,000 billions and a billion's 1,000 millions, maybe that's easier for you to conceptualize. Okay. One thing you'll need to be doing in these lab reports, at least a couple of your lab reports this semester, is to convert between the two types of uncertainty. It's very simple. Don't overthink it. Think it. It's easier than you think. If you know how to take the percent of something or a percentage of something, then you know how to do it. So if you're like me and you're a smart shopper and you know something's 10% off and you try to do a little mental calculation in the store, you're basically doing the same thing here. What I've written here is absolute uncertainty equals, what's this quantity in parentheses? Well, absolute uncertainty divided by the thing you're measuring, that's what we call relative uncertainty. So I've enclosed the relative uncertainty in parentheses. Just multiply the relative uncertainty by the thing that you measured, and now you have absolute uncertainty. And hopefully it's clear why that works. This is just like algebra, right? The x and the x cancel. So that's why this is an identity. If you cancel the x's, you get delta x equals delta x. So x is short for x best, really. It would be your best estimate of x. There it is. If you happen to know the relative or percent uncertainty in a measurement, just multiply that relative uncertainty by the thing you're measuring, and that converts it back into an absolute uncertainty. If you've got this expressed as a percentage, it's like saying, well, what's 4% of that 22 centimeters? 4% is 0.04. You just multiply 0.04 times 22. So let's do an example here. Let's say you stand on the scale. It says you're 176 pounds, but because you're a nerd, you actually have the manufacturer's manual and you read it, and it tells you that this scale has a precision of something like 1.5%. Okay, what's the range of likely values for your body weight? You may not be exactly 176 pounds, right? Just because the scale said it, it could be off by a couple pounds. Now, are you going to be 250 pounds and the scale says 176? That would be a horrible precision. That would be a useless scale. So let's see what the numbers come out to be with this reasonable relative uncertainty of 1.5%. I'm going to use the letter W now instead of L or X. W for weight. So the absolute uncertainty in your weight would be the relative uncertainty, which I've enclosed in parentheses, times the best estimate for your weight. So the scale told you 176, that's its best estimate, but the manual that came with the scale tells you that it could be off by as much as 1.5%, and I just made that number up. So take 1.5% of 176. Notice I wrote it as 1.5 per 100. You could have written it as 0.015, and I get 2.6. All right, so that's like saying your weight could be 176 plus 2.6, or it could be 176 minus 2.6, or anything in between. So just like with the soccer ball earlier, we'd like to express that in this form, the best estimate plus or minus the, what's this called? Absolute uncertainty. Let's put it all in parentheses so that we can put the units pounds on the outside. And there it is. This would be a perfectly valid way to state your result. You could also go ahead and subtract and add 2.6 from the best estimate to get the left and right ends there of your likely range. So what you're saying is most likely your weight, your true weight, would lie somewhere in this range. Now, is it impossible that your true weight would be 179 pounds? Because that's outside this range. It is possible because this whole process is approximate. Possible, actually very possible that it would be 179 pounds because this was just estimated anyway. When the manufacturer told you that the precision was 1.5%, even that number is approximate, it's an estimate. Now, assuming that this thing was manufactured correctly and that it's got good batteries in it, if it's an electronic scale, is it possible that your true weight is 250 pounds? That's very unlikely. The scale would have to be defective. I think you get the idea. And because of how much approximation is involved in these numbers to begin with, there's no real need to keep this last digit here. Why not just round to the nearest pound and state the range like this? Now, this result or this statement may have a little bit more information in it than this, but they're both acceptable. You wouldn't want to round to the nearest tens. I wouldn't say it's between 170 and 180. Then you're definitely throwing away some of the information that you have. But this ought to be fine. Don't stress too much about how many digits to keep. I may talk a little bit later about number of significant digits, or sig figs as some people call them. But the whole thing is approximate. All the rules that you use are just to bear in mind. I'm not going to say order of magnitude uncertainties, but like, let me put it this way. Would it make any sense to say that the upper limit on your weight could be 178.655555243? There's no way you can know the upper limit with that kind of precision. So just pick a number of digits that's reasonable. You could also just say it like this, right? You could just leave the uncertainty as a relative uncertainty. If you put a percentage here, see how there's pounds here, no pounds here. That's because this is a relative uncertainty. That's what the percent sign is telling you. And for some people, this is fine too. I mean, that's pretty informative as well, is it not? To say that your weight is 176 pounds plus or minus 1.5%. If you want, you can get your calculator and plug it in, figure out what 1.5% of 176 pounds is. That's what we did previously. But these are all valid ways of writing it. I think I prefer one of these, but if I happen to see something like this on a lab report, as long as you've got that percent sign and there's no inconsistency there, that would be acceptable as well. So estimating and then expressing these two types of errors, absolute and relative, that's the first thing you need to know about this process. But perhaps more important or equally important is to understand the propagation of uncertainty. So this graphic is not something you need to understand at the moment, but you'll look back later and know what it means. Let's choose as an example two people who, this is totally contrived, stupid example, but it works. Let's say these two people want to go on a carnival ride, but there's a weight limit for your combined weight for safety reasons. So Alfred and Betty need to know their combined weight, so they each step on I said bathroom scale, but this guy is on a physician scale, more precise. I'm going to use the letter A to represent Alfred's weight, and B for Betty's weight. All right, and since these are fictional people, nobody has to get offended here. I've just picked reasonable numbers. I'm going to express Alfred's weight with an absolute uncertainty. So I'll put a best estimate plus or minus, and you know what? I really should have plus and minus here. I'll go back and fix that. This should say plus or minus and plus or minus. And here are the numbers I chose. Maybe Alfred's 210, but because he's using a fairly precise scale, I really should have gone with an even smaller absolute uncertainty, but that works. He's 210 plus or minus some possible absolute uncertainty. You know, maybe if you don't use the scale quite correctly, or if you weren't real careful with your measurement. Same thing for Betty. I'll go with a lower weight, but the same absolute uncertainty. Besides, those bathroom scales aren't terribly precise anyway. And the question is, we've estimated their, or they've estimated by measuring their weights individually. We'd like to figure out what the best estimate is for their total weight, and then what's the range of possible values for their total weight. And it's a very simple thought process here. I'm sure you see where this is going. So I will first ask, what's the highest probable value for their combined weight? Just remember, each of these equations here gives you the range of likely values. Just because the scale says 210 doesn't mean Alfred weighs 210 pounds. He could easily be 211.5. That's a very likely value. Now, is he likely to be 215? Not if the scale was manufactured correctly and he's using it properly. So let's go with since we're adding their weights, right? We're going to take the two numbers and add them together. Let's go with the highest possible value for Alfred's weight and the highest possible value for Betty's weight. We'll just add those together. And I'm trying to do that symbolically here. The maximum likely value of the sum of their weights would be the maximum likely value of Alfred's weight plus the equivalent number for Betty's weight. Well, in terms of the uncertainty, remember this is supposed to say plus or minus here, the highest probable value for Alfred's weight would be that 210 plus 105, like if we're on the high side there. Same thing for Betty, but then we can just move stuff around here. Let's put the two best measurements in parentheses and put the two individual absolute uncertainties in parentheses. And then A best plus B best, well, wouldn't that just be the best value of A plus B? Your best estimate of their combined weight would simply be your best estimate of Alfred's weight plus your best estimate of Betty's weight. And then we can ask a similar question, what's the lowest probable value? Well, this statement says that Alfred could very possibly be as heavy as 210 minus 1.5. So in other words, 208.5. And Betty could be as low as 166 minus 1.5. So the minimum likely value of their combined weight would just be Alfred's likely minimum weight, and same thing for Betty. And I realize I'm being very deliberate here. We're going kind of slow here. It won't always be like this, but I want to make this clear for your 2 or 3 labs that you'll be doing that require this stuff. Okay. Just like before, let's move stuff around. And I factored out a minus sign here for the two absolute uncertainties. And we see that it's the same as the previous expression. Let me go back a slide. The only thing that's changed is this plus sign turned into a minus sign here. So to summarize, this formula will give you the lowest likely value of their total weight in terms of their best estimates and the uncertainties of each individual weight. Well, let's compare that now. Let's introduce this letter Q. I'm going to let Q equal this quantity that we calculate from the two measured quantities. So A and B are measured. We plug them into a formula to calculate a third quantity. In this case, the formula is really simple. It's just A plus B. But here's what we'd like to do now. Q is the quantity that is calculated. We would like to state our best estimate for that calculated quantity, plus or minus its own absolute uncertainty. So this will be the absolute uncertainty in total weight. So now we get to the somewhat interesting question. If the uncertainty in Alfred's weight is 1.5 pounds, and same thing for Betty's weight, well then what's the uncertainty in their total weight? And there's a couple different reasonable answers to that. You might be thinking, well, it's probably just 1.5 pounds as well. Or you might be thinking, well, what if both measurements are off? Those errors should compound. Maybe it's as high as 3. And for now, that's actually the answer I'm going to go with. Later, we'll have a somewhat better answer. But if you just compare this general formula for any measurement or any calculated quantity, plus or minus uncertainty, compare that to the two results previously, we see that the best estimate for Q, of course, is just the sum of the best estimates. And then this is the answer we were looking for. Since it's plus or minus some fixed delta Q, here we've got minus this quantity in parentheses, and down here we've got plus this quantity in parentheses. So evidently, this quantity in parentheses is what we can identify as delta Q, because we're subtracting it to find the lowest likely value, and we're adding it to find the highest likely value. That's exactly what delta Q is. So there it is. The very simple formula for the uncertainty in the sum of these two measurements is simply the sum of the uncertainties. Right? Not terribly exciting, but hopefully reasonable to you. If Alfred's weight could be off by 1.5 pounds and Betty's weight could be off by also 1.5 pounds, then their total weight might be off by as much as 1.5 plus 1.5. Okay, so that's the rule that you would use anytime you're calculating the sum of two measurements. Well, it turns out we almost never use the sum of two measurements in the labs that we do. It's almost always multiplication and division. So we'll look at that in a moment. Just be aware of this rule though. And here's a very important term. Delta Q, or vocabulary term. Delta Q is the uncertainty in that calculated quantity. You don't measure Q directly unless you were to put them on the same scale. If you had a large scale, you could put them on there directly. We have to make the measurements separately and then add. So we say that the individual absolute uncertainties, the errors in those individual measurements, propagate to an error in the final quantity. So delta Q, the error in Q, that's called the propagated uncertainty. Look up the definition of the word propagate. Maybe that'll make more sense to you. But both of those measurements contribute to the uncertainty in the final quantity. We call that uncertainty the propagated uncertainty or propagated error. You could use either term. Okay, so my best estimate for their combined weight, I just add the two best estimates for their individual weights, and then we add the two absolute uncertainties, and we get this statement. Their total weight is likely 376 pounds plus or minus 3 pounds. And then, of course, you could write it that way if you prefer. But let's move on to the more practical case. What if the quantity that we're calculating is actually the product or the quotient of two measurements? Measure these two things and then multiply them or divide them. And this is more flexible because anytime you're adding two things in the physical sciences, you have to be adding two things with the same units. You can't add a weight to a time. I can't think of a single example of when you would ever add a weight and a time, or a mass and a distance. It's like comparing apples to oranges. But you can certainly multiply mass times velocity, for instance, or force times distance. We do that a lot in this class. So here is the rule that works. And you can use calculus to show where this rule comes from. I won't do that yet. But basically, this is called the total differential of a number that's a function of two other numbers, two other variables. So instead of saying that delta Q is just the sum of the absolute uncertainties, which was the case previously, in this case, because we're multiplying or dividing, it's actually the same relationship, but between the relative uncertainties. So this is the one that's more worth memorizing. If you happen to know the percent or relative uncertainty in your two measurements, all you have to do is add them to get the percent uncertainty in their sum. Okay, so it's a lot like the previous rule, but you must use relative uncertainties. Aha, let's do an example for a moment. I think a good example would be to suppose that you were out walking and you just were interested in estimating your average walking speed. Now, I think a human being walks leisurely at like 2 or 3 miles per hour. So I'm just going to pick random numbers here. If they come out unreasonable, I apologize in advance. But if you are moving at constant speed, then we know that your speed, which I'll call v for velocity, is just the distance you travel divided by the time in which you do it. So a car may be driving 65 miles every 1 hour on the freeway. So I'm just going to estimate some numbers. Let's see here. 3 miles per hour would be 3 miles every 60 minutes. So, okay, I think I can pick something somewhat reasonable. Maybe you've got one of those Fitbits on your wrist, or how do you actually know how far you walked? Whatever, you're at the track and you know that one lap is something like a quarter mile. Suppose your distance is estimated to be 3 miles. You spent some time down there in the evening, and you walked a good 3 miles around the track. And I'm going to go with 3.0. And then we need to pick an uncertainty for how much distance you actually walked, because a lot of tracks, for instance, it's really, isn't it like, what is it, 400 meters around the track, which isn't exactly a quarter mile. So you're not totally sure that the distance you walked was 3 miles. Let's say you could be off by as much as 0.3. I'll go with 0.4 even, 0.4 miles, right? You think you walked 3 miles, but because you're not exactly sure the distance around the track, it could be something like 3 miles plus or minus 0.4. So this would be the absolute uncertainty. And you think you did that in a time, well, you can walk easily. You can walk a mile in 20 minutes. So I'll go with, since that's multiplied by 3, I'll go with 58. Maybe you were walking kind of briskly. 58 plus or minus. Now, you weren't real observant of your watch, let's say. You're not exactly sure what time you started, because maybe you remembered to look at your watch after you had already started walking. So I'll say 2 minutes in. You could be off by as much as 2 minutes. And I'm realizing normally we express speed in miles per hour, but I've gone with the units of miles per minute. So I'm going to do this whole problem in those units, and at the end I can convert to miles per hour. So don't be confused by MI for mile and MIN for minutes. And we'd like to find the best estimate for the speed, and also a possible range of values, delta V, all right? This is what we're interested in. We need to know this number and this number. And I'll say in miles per hour. A lot of times you see that written MPH, which is informal. It's a little clearer if you express it as a ratio of miles per hour. So I'm going to do this in miles per minute first. V best, our best estimate, well, we would just take our best estimate for the number of miles and divide it by the best estimate for the number of minutes. And then I could just do this right now. I can convert from minutes to hours right now. So I know that 1 hour has 60 minutes in it last time I checked. MIN up top. So if we take 3 times 60 and divide by 58, how many digits should I keep? The calculator's spitting it out a whole lot of digits. Well, you know the rule. If you're multiplying or dividing, just go with I think it's the least number. Yeah. So I've got just 2 digits here. I'll keep 2 digits. I'll round this to 3.1. 3.1 miles per hour. That's my best estimate for walking speed. So that's a reasonable number. But what's the likely range? What's my absolute uncertainty? Well, remember, if you're multiplying or dividing measurements, you can't simply add the absolute uncertainties. What you would actually do is add the relative uncertainties to find the relative uncertainty in V. So before I called it, my measurements were A and B, and we used those measurements to calculate something called Q. Well, now my measurements are D and T, and I'm using them to calculate V. So the rule that I'm going to use is this one. The relative uncertainty in the speed is the sum of the relative uncertainties. Now, if you happen to know these numbers in advance, that makes it really easy. Suppose that you only knew the distance you had walked to the nearest 5%, and you only knew the time to the nearest 2%. You just add them up, and you would say that the overall speed, or your estimate for the speed, is uncertain by as much as 7%. You just add the relative uncertainties. As long as they're both percentages, you can add them. In this case, we don't know the percent uncertainties directly. What we're given, or what I gave you, was the absolute uncertainties. So the first thing we need to do is to convert these absolute uncertainties into relative uncertainties so that we can plug them into this expression. And the nice thing about that here is when we plug in minutes over minutes, we get something that's dimensionless, which means we don't actually need to convert into hours. If I were going to convert each of these times in minutes into hours, I'd have to divide them by 60. That means I'd have a factor of 1/60th up top and 1/60th on the bottom, and they would cancel. So that's a nice thing to remember, is that when you've got a ratio of two quantities, there's no need to convert. All right, so delta d over d. The relative uncertainty in the distance would be that 0.4 miles compared to 3 miles. And again, you see that the units cancel. Relative uncertainties are dimensionless. 0.4 divided by 3. Now I could write down 0.13. No need to keep all these threes. But I think that I'll go ahead and turn that into a percentage right now. I'll multiply by 100 and say that's basically 13%. So your measurement, your estimate of the distance you walked is uncertain by 13%. You could even, honestly, you could even round that down to 10% because this whole thing is approximate anyway, but I'll keep the 3. And the uncertainty in the time walked, no need to convert. That would be 2 minutes compared to 58 minutes. Well, that's close to 2 over 60, is it not? And 2 over 60 is 1 over 30. And let's see, 1/30th, that's kind of like, now my mental math is failing me now, so let's use the calculator. 2 divided by 58. I'm going to multiply by 100 again. 3.4%. Okay, so now we just add them and say that the relative uncertainty in the speed is just 13 plus 3.4%. And rather than say equals, I'm going to put an arrow because I'm going to round. I don't think we really need this 4. Let's just call it 3. 13 plus 3, 16. I could even call it 15 since we like multiples of 5. Okay, so my calculated speed could be in error easily by as much as 16% because it comes from two measurements that are also not particularly precise. We say that the uncertainties in our estimated quantities propagate to cause an uncertainty in our speed. I mean, think about it. If you don't know your distance any better than 13%, and your time could also be off by as much as 3%, then of course your calculated speed is also uncertain as well. Okay, how do we convert this 16% back into a relative error? Because remember, the result we're looking for is this. We'd like to state it as v best plus or minus an absolute uncertainty. This has units. If we're going to write the speed in miles per hour, then we need to write the uncertainty in miles per hour. So here's where we do this. So I'll just remind you, delta v would be delta v over v times v. Now technically this is v best. I'm going to plug in the 3.1 miles per hour, but you see how the v's cancel? We got delta v equals delta v. So I really just need to take 13%, which I'll write as 0.13, 13% of 3.1 miles per hour. And I'm being careful to include units as I go here. 13%, that's dimensionless. There are no units associated with a relative uncertainty. Can I do that in my head? 13 times 3, what is that, 39? Then I have to move. So that's like 0.39, which I could round to 0.4, but let's do it with the calculator. 0.13 times 3.1. I'm just going to round that to 0.4. So 0.4 miles per hour. And that means it would now be reasonable to say that your speed was likely 3.1, but it could be as much as 0.4 higher than that or 0.4 lower than that. Arguably, you could just round this to 3 and say it's 3 plus or minus 0.4. I think this is perfectly fine. No need to sweat too much about which digit to use exactly. Now, we might as well subtract and add 0.4 from 3.1. So we could say 2.7 miles per hour is less than or equal to, v is less than or equal to 3.5. That makes it really clear what the lowest likely value is and the highest likely value. Is it possible that you were walking as slow as 2.6? Sure. not terribly likely, because if you did a good job of estimating these numbers, then your true value for your speed should lie within this range, but it might be slightly out. Now, how likely is it? If you estimated these numbers well, how likely is it that your actual speed was 6 miles per hour? Very unlikely. In fact, we know that because people can't walk that fast without looking really weird. You'd have to be totally unconcerned with how other people perceive you if you want to go out walking on the track at 6 miles per hour. I don't even know if that's possible. Okay, let's put a check on this formula here. Where is the formula? Did I actually write it down? I did not. Let's check that this result is legitimate, because I just gave it to you a few slides ago. I said that the appropriate rule is to add the relative uncertainties, and then at the end you can convert relative uncertainty back into absolute uncertainty. Is there another way we can check what the highest likely value is and the lowest likely value? Well, since this is our formula for speed, if you plug in a bigger value for d, since it's in the numerator, doesn't it make the speed come out bigger? And if you plug in a smaller time, a smaller denominator would also make the velocity come out higher. So if we want to figure out what the largest likely value is for your walking speed, let's put in the largest likely value of the distance you walked and the smallest likely value of the time to make this as large as possible. So I'll say Vmax for this particular case would be max probable value for the distance divided by T min. So I'm just kind of using common sense here to get another, or to find the highest likely walking speed by another route. Well, the highest likely distance that you walked would be 3 plus 0.4. So you may have walked as much as 3.4 miles, and you may have done so in a time of 58 minus 2. It's possible that you did it in as little as 56 minutes. And of course, I'll convert from minutes to hours so that our speed comes out. Now, what number are we hoping comes out here? If this formula that I've quoted is legitimate at all, then the number that it gives for the lowest likely speed should be similar to what I get right now. So let's see what happens. 3.4 miles, 60 minutes in an hour, 56, okay. Oh, I'm checking the other one, right? Yeah, I'm checking the 3.5, right? I'm doing the highest likely speed, and I get 3.6. Okay, so just by using common sense and plugging in reasonable numbers, I get a number very close to what I got using this more formal method. So that's reassuring. I'm not going to kill another tree. I'll use the backside here. What about the lowest likely value for your walking speed? Well, you may have walked, let's see here. If you plug in your lowest likely distance and your highest likely time, that would give you the lowest likely value for your speed. You may have walked as little as 3 minus 0.4 or 2.6 miles. Did I do that right? What was my, yeah, 3 minus 0.4. And it may have taken you as long as 58 plus 2 minutes. Convert from 60, or convert from minutes to hours. And that's just kind of a coincidence that we've got two factors of 60. So that came out real easy, 2.6 miles per hour. So just by plugging in numbers, 2.6, how does that compare to 2.7? Pretty darn close. So the other way we found 2.6 miles per hour is less than or equal to the speed is less than or equal to 3.6. The agreement there hopefully gives you some confidence that this formula does a pretty good job. And actually, we're going to see that that there's another formula that does an even better job of getting us a range of values. So we'll get to that shortly. Many of the formulas that you'll encounter in this class and the subsequent classes are not as simple as just multiplying two numbers together. And I should have pointed out there, oh, I guess I did. It may be surprising to you that the formula works the same for A times B as A divided by B, but it does, and you can justify that with calculus. The example we just did was division anyway, distance over time. Okay, so what happens if you're multiplying and or dividing more than two quantities, and maybe those quantities have exponents next to them? So in general, here's an example. What if you've got a measured quantity A, maybe you're measuring a time that you're calling A, and a distance that you call B, and a mass that you call C, and each of those numbers is being raised to some power. What are we supposed to do then in order to estimate the uncertainty in our calculated quantity? If each of these are measured quantities, they're all subject to their own absolute uncertainty, and that's going to cause a propagated uncertainty in the thing that you calculate. If you're not totally sure of the values of these quantities, then you cannot be totally sure of the value of Q. So it turns out that the formula we're going to use looks very much like the previous one. There's just one little thing we have to tack on there. We're going to weight each measurement's uncertainty according to the power to which it's raised, which kind of makes sense. Like if you're raising something to the 5th power, then any uncertainty in that measurement is probably going to be a bigger deal than something that's only raised to the 1st power. So there it is. It looks a lot like the previous formula. Previously, we only had 2 measurements, A and B, and both of those numbers were raised to the 1st power, right? If it's A times B, that's really A to the 1st, B to the 1st, or A to the 1st over B to the 1st. But now we've got these exponents here that we're going to put out. So do you see how if this measured quantity was being raised to the 5th power, you'd have a greater weight out front than a quantity that was being raised to the 1st power in your formula. Now, also, I didn't put this in the slides, but if you have numbers here, like if your theoretical formula includes the number 2 out front, or pi, those numbers have no associated error. A number is a number. It's supposed to be precise. So you don't even have to worry about it. It doesn't appear in the formula at all. Your first lab where you're going to measure the density of water, a factor of pi is going to appear in your formula. When it comes time to implement this expression, you don't even worry about the pi. There is no uncertainty in pi. So for a concrete example, one of the formulas that you'll be using often later in the semester is the formula for the kinetic energy of a moving object. Anything moving that has mass has energy associated with that motion. Many of you have seen this before. You just take the mass of the object, you multiply by the square of the speed, and then you divide by 2. Well, the speed may have been calculated as a distance over a time. So arguably, there are 3 different measured quantities that go into determining this 4th quantity which you calculate. You don't measure kinetic energy directly, usually. You measure it, or you calculate it from 3 quantities which were measured directly. So we'd like to know, how do the uncertainties in these 3 measurements propagate to produce an uncertainty in K? Because when you put your object, if it's a baseball, and you put it on one of the scales in the chemistry department to measure its mass, there may be some, or there is some uncertainty associated with that measurement. So the formula is real easy. I've got 1, 2, 3 quantities. That's why you see 1, 2, 3 quantities in parentheses. But out front, I've weighted them according to their powers in the formula. So since distance is being squared, I put a 2 out front. That's the exponent. Same thing for time. Mass is being raised just to the 1st power, and we don't need to write that. That's it. But please observe, what type of errors are we relating here? This is a relative error. Mass would be kilograms over kilograms. They're dimensionless. Excuse me, if you're looking at a dimensionless error quantity, that's a relative error. So we can calculate the percent, pardon me, or relative uncertainty in the kinetic energy just by knowing the relative uncertainties in the 3 measured quantities. So we should do another example of that. So yeah, I'm reminding myself here. And I'm going to move a little quicker with this example, so I'm not too pedantic here. I won't pick units. I'll just make up a formula. So this is not based on anything in our actual class. Let's say this calculated quantity Q depends on the cube of A and the square of B. You know, I'm writing too small here. Cube of A, square of B, and maybe we're dividing by the 5th power of C. And here's my best estimate and my absolute uncertainty for A. I think it's the number 12 plus or minus 1. Again, normally in a physical science class, there would be units associated with this quantity because it's something that you measured. But I just want to show you how the formula works here. And maybe B is 51 plus or minus 3. And lastly, C, let's go with the decimal. How about 2.75 plus or minus 0.8? And I'm just pulling these numbers out of a hat. Okay, find your best estimate for Q and the absolute uncertainty. So what's the range of likely values for Q? Since we know the range of likely values for these three measurements, what's the range of likely values for Q? Hey, if you're feeling confident, pause this video. I feel like such a hack saying this. Pause this video and give it a try by yourself. Or just watch me here. First, I need to figure out what all my relative uncertainties are, because since we're multiplying and dividing, we're going to be adding relative uncertainties, not absolute uncertainties. The relative uncertainty and you know what? Let's just do it all at once. The relative uncertainty in Q is the following. Well, we're going to have three relative uncertainties that we're adding together, since there are three measurements. And then we're going to weight them all by their exponents. So A is being cubed. So I'll put a 3 out front for A. B is squared. So here's the 2. And lastly, C gets a 5 in front because we're raising it to the 5th power. Now, the uncertainty, relative uncertainty in A would be delta A divided by A. That's the absolute uncertainty of 1 divided by the value of A, the best estimate for A, which is 12. And then for B, we've got an absolute uncertainty of 3 compared to its best estimate of 51. And lastly, C is uncertain by 0.8 compared to 2.75. And here's a good tip when you're doing actual labs in the future. Rather than evaluate this all at once in the calculator, it's kind of nice to evaluate them individually, because that will tell you which of your measurements sucks the most, which one you need to improve first if you want a more precise measurement of whatever it is that you're determining here. Like if you find out that this uncertainty is 10 times as large as these two, that means you need to find a better way to measure this quantity if you hope to improve your final calculated quantity. All right, as I was going through all these numbers, I discovered that I had made a clumsy choice of uncertainties for two of the measurements in particular. 1 compared to 12 is not so bad and for a relative uncertainty, but once you multiply by 3, that becomes, this is really a 25% error, is it not? Which is unrealistically large. Why would you be doing measurements that uncertain in, at least in the classes, in the labs that you would be doing in this class? So I really need to modify these. Let's go with 12 plus or minus 0.3. And that means I should really write this as 12.0 to indicate that there's some kind of precision here in this first decimal point. I'll leave this one, I'll make this even smaller as well. Let's go with plus or minus 1. And I just fixed this one. Originally it was 0.8. 0.8 compared to 2.75 times 5 meant just much too large of a propagated uncertainty. So with these corrections, let me recalculate my propagated relative uncertainty. So right now I'm just evaluating everything as a decimal fraction. I have not converted to percent uncertainty yet. So we've got, for A, we have an uncertainty of 0.3 compared to 12, but we have to weight that by the power of 10, which is 3. And then for B, we've got an absolute uncertainty of 1 compared to 51, which must be weighted by the power of 2. And lastly, we weight with the number 5, an absolute uncertainty in C of 0.08 compared to 2.75. And here's where before, I'm sorry, that was out of frame. before summing all of these terms, I'd like to evaluate them individually to see which contributes the most to the propagated uncertainty. So 0.3 divided by 12, and then I multiply by 3. 0.075, I'm going to go ahead and convert to a percent error right now, multiply by 100, and that 0.075 becomes 7.5%. 2 divided by 51, if I round, that's about 4% uncertainty. And this last one, yeah, that factor of 5 brings us up to a 14.5% uncertainty. So none of these contributions is wildly greater than the others, but there's a clear culprit here. If you were going to improve your determination of Q, the first measurement you would want to improve would be the measurement of C. So can we do these in our heads? 14 plus 7 is 21, plus another 1 from the 0.5%, so 22, roughly 26. Let's just round. We can call this 25%. Not terribly precise, that kind of uncertainty. That's the relative uncertainty in Q. Let's now convert that into an absolute uncertainty. In order to do that, we first have to know what Q best is. To get our best estimate for Q, we would just plug in our best estimates for A, B, and C. Those are the numbers given here. So that would be 12 cubed times 51 squared, and we divide by 2.75 to the 5th power. Let's see what our best estimate for Q is. 12 cubed times 51 squared, lastly divided by 2.75 raised to the 5th power, and I get, okay, that's a big number. How many digits am I working with here? A lot. Let's keep 2 or 3 digits, since each of these numbers that we're plugging in has 2 or 3 sig figs. So I'll round this to 28,600. See the 28577 in the decimal point. So this is, I'll round it to 29. Yeah, 28,600. That's my best estimate to an appropriate number of significant digits. Now that I've got my best estimate and I know my relative uncertainty, I can find the absolute uncertainty. All I have to do is take the relative uncertainty and multiply by the best estimate. In other words, take 25% of 28,600. Normally, each of these quantities would have units associated with it, but I just want you to see how the numbers work out. 28,600 times 25%, and I'll round that to, well, I'll just keep all those digits, 7,150. Okay, so Q should be in the vicinity of 28,600, but it could be 7,150 on either side of that. And here's where I'm going to take a look at the last digit here. Since we only know this number to the 100ths place, there might not be much point in keeping the tens place here. So maybe I should just call this 7,100 or even just 7,000, since this whole process is approximate anyway. So now what I'd like to do is find the lowest probable value for Q and the highest probable value using this statement. So if I subtract 7,100, I find that Q, realistically, Q could be as low as 21,500. Normally, I would have units here. And it could be as high as 7,100. So there's a very broad range of likely values for Q. That's because I picked rather large absolute uncertainties for these 3 fictional measurements. Okay, what are we doing here? I'm trying to convince you that this formula is legitimate. This is the highest likely value and the lowest likely value using this expression for the propagated relative uncertainty. So you have no reason to believe at this point that that formula is legitimate. Is there another way we could use common sense to get the highest and lowest likely values? Let's go back to the formula here. Another way, just to convince ourselves that this formula works. Well, the max likely value of Q would be the one where we plug in the max value of A, the max likely value of B, and the minimum likely value of C, because C is in the denominator. See what I'm doing? The same thing I did previously. So the highest likely value of A would be 12 plus its absolute uncertainty. So 12.3, I'll cube that. B could be as high as 52, taking into account the uncertainty. And the lowest likely value of C would be 2.75 minus the 0.08. 2.75 minus 0.08, should be able to do that in my head. So we'll divide by 2.67 to the 5th power. Now, because I've got these large exponents that I chose, I don't expect the agreement between the previous method and this method to be as good as it was in the last example, but we'll see. 12.3 cubed times 52 squared divided by 2.67 raised to the 5th power. I get 37,000, and I'll round it to 80, which is significantly higher than 35,000, but the difference between these upper ends is not as great as the range of the value. So I'm still somewhat pleased with how this is coming out. Q min, what's the lowest likely value of Q? Well, we would plug in the minimum likely values of A and B, and this time the maximum likely value of C. So the lowest likely value of A would be 12 minus 0.3, cube that, and the lowest likely value of B would be 50. And then we'll divide by the highest likely value of C, 2.75 plus 0.08. Raise that to the 5th power. And we'll see how this number compares to the lower likely value obtained by our previous method. So 11.7 cubed times 50 squared divided by 2.83 to the 5th power. And that comes out to be 20,000, basically 60. Oops. Excuse me, 22,000. Okay. So two different methods for approximating the range of likely values of Q based on our estimates for the uncertainties in the 3 measurements that determine Q. And this lower limit does not agree exactly with this lower limit, same thing for the upper limits, but they're fairly close. Also keep in mind, we are going to amend the method used first of all. We've got a better formula coming up, and maybe those numbers would agree a little bit better. But remember, this whole process is approximate anyway. I mentioned just a moment ago that we're going to improve the formula. The formula that you've been using, or that we've been using here in the video, tends to overestimate the propagated error or uncertainty. In fact, you might say it's a little pessimistic. So let's see if we can come up with a more realistic formula. Let's go back to the very simple case where your calculated quantity is just the sum of 2 measurements. And I'm going to introduce some notation here that's only pertinent to this video. You don't need to memorize this right here. This is, let me get the laser pointer. This right here is not something you'll see elsewhere. It's just for the purposes of this discussion. So delta Q sub A is the part of the propagated uncertainty that's due to the uncertainty in A. It's the contribution from the uncertainty in A. Similarly, delta Q sub B will be the contribution to the overall propagated error due to any uncertainty in measuring B. So this is not mathematical. What I'm about to do can be justified with statistics, but here's a nice way of thinking about it. Think of this plane as representing all the possible values of Q, all the possible values that one might calculate for Q by plugging in A plus B. And let's let this dot represent the true value. Like going back to Alfred and Betty, there is some number in the universe that describes their actual combined weight. Think of this dot as representing that number. Now, in order to calculate that number, you have to plug in Betty's weight and Alfred's weight. Now, if you measured Alfred's weight in error, let's say his scale gave a number that was a little on the high side. When you plug in that number A that's a little too big, it's going to tend to pull your calculated Q away from the true value. So if this is their actual true weight, the uncertainty in Alfred's measurement tends to pull it a little to the high side. So you would come up with a value of Q over here instead of the true value. So delta Q sub A is that contribution. Now, what if Betty also used a scale that tended to give her a number that was a little on the high side? So you're plugging in a value for A that's a little too high than it really is, or a little higher than it really is, and you're plugging in a value for B that's also a little higher than the true value for Betty's weight. So in other words, those two errors add, in a sense, they both sway the result in the same direction. And so this black arrow here, which has a length equal to the sum of these two, represents the total propagated error or uncertainty in Q. So if this dot represents the true value of their combined weight, what you would have calculated is a number over here due to these two contributions to the error. Now, it doesn't have to work out that way. If Alfred and Betty are using two different scales, maybe Alfred's on a scale that tends to give you a number that's a little too high, and Betty's scale has a systematic error that tends to give a result that's a little too low. Then this is what would happen. Alfred's error pulls the calculated Q to the positive side, but then if Betty's measured weight has an error that it gives a value that's a little lower than the true value for Betty's weight, then that's going to tend to subtract from Alfred's error. So in this case, the two errors do not work together, so to speak. They work against each other. They tend to cancel to an extent. And now you've got a much shorter black arrow representing the net propagated uncertainty. So which of those two scenarios is more likely? Well, in a random situation, if it's just two measurements going in, they're equally likely. So it would be nice to come up with the graphic and hence a formula that captures the intermediate or compromise scenario. So this is the best case scenario, is that your two errors tend to cancel each other out. The worst case scenario is that your two errors compound each other. Can you think of any way of drawing these three arrows together to get a delta Q that's intermediate in length? This is a really long delta Q. This is a short delta Q. How can we arrange these to get a delta Q that represents, the average case? Sometimes the errors add, sometimes they subtract, and it's not just two measurements. What if we were calculating a Q that depended on 10 measurements? What are the odds that all 10 errors will be in the same direction? Very low. So there's going to be some cancellation in the general case of a Q that depends on several measurements. So here's one thing that works. Make a right triangle out of them. And of course, this is purely symbolic, representative, whatever the word is that captures what I'm trying to communicate here. But if you put them at right angles, delta Q sub B and delta Q sub A, then you get a hypotenuse that's intermediate in length between the best case and the worst case scenarios. And that is very suggestive of the Pythagorean theorem. So why don't we combine these two contributions to get a formula for delta Q that represents kind of the average situation where you've got some cancellation of errors. In other words, we add them in quadrature, as it is called. And this is an old word in math and science. This word quadrature connotes right angles. Anytime you see that word, it's supposed to capture that idea of a right angle. So we add them in quadrature, which really just means add them the way you add numbers in the Pythagorean theorem. And I realize there's a typo here. This should say squared, so I'm going to have to fix that. All I've done is apply the Pythagorean theorem to this triangle in order to get this formula here. So previously, for the case of, I goofed again. This is the wrong formula, is it not? You would only add relative uncertainties if you were taking the product of A and B. I used the simple case of A plus B just to demonstrate the idea there with the addition and quadrature. But let's go back to the more useful case of a product here. We know that previously we would have just added the relative uncertainties to get the relative propagated uncertainty. This time we're going to add them in quadrature. So instead of just summing them, first we square the terms, square the separate relative uncertainties, then we add them, and lastly we take the square root. It's just like Pythagorean theorem, and it would actually work no matter how many measurements went into the calculation of Q, as long as it was just multiplication and division. So if we were to apply this to an actual example, I'll go back to the case of kinetic energy. If we had measured an object's mass the distance it traveled, and the time of travel. Each of those three measurements would have its own associated, and let me get the laser pointer, it would have its own associated absolute uncertainty and hence relative uncertainty. And a moment ago, I said that you would just sum all the relative uncertainties and weight them according to their exponents. Now, we're just going to tweak it a little bit to get our new and improved formula. This is a less pessimistic formula. This does not suffer from the defect that this formula suffers from, which is to overestimate your propagated uncertainty. So take each of these terms, square them, add them up, take the square root, and note, even though the 2 is outside the parentheses here, the 2 is inside here. You got to take the whole thing, square it, add it up, and then take the square root. And the best way to get comfortable with this, of course, is just to do an example. So I will do one in a moment. And that moment is here. Let's take the example of somebody on a bicycle riding along a track, a running track like we did just previously. 1/2 times the mass times speed squared, but we'll assume that the speed was calculated as a distance over a time, and then we square all that. Whoops. Okay, let me try that again. 1/2 mass, that's supposed to be a 2, d squared over t squared. I will pick values for each of these quantities, and I will pick absolute uncertainties, and then we'll just run through this process. And this will be the last tedious example from this video. Suppose that the mass, since it's somebody on a bicycle, it can't be more than, I'll go with something like 130 kilograms. And let's say we're unsure of the mass of this bike plus the person on the bike by maybe 2 kilograms. And then maybe you were just watching this person ride their bike along a 100-meter dash, that's straight section of one side of the track. So you tried to stop your stopwatch and start your start. Well, that's difficult to say. You tried to start and stop your stopwatch. How come it's a stopwatch and not a start watch? I never thought of that. It's kind of asymmetric there. You try to start and stop your start watch at the beginning and end of those 100 meters as best as you can, but maybe you're off by 1/2 meter if you were being really careful. Okay. So 1/2 meter is the absolute uncertainty in your measurement of the distance that this person traveled on their bicycle. And I know a person can run 100 meters in 10 seconds. So they should be able to ride 100 meters in, let's say, 7 seconds, I would think. And usually measurements of time, especially if you're using a stopwatch, are not particularly precise. So we're probably off by at least 0.4 seconds. All right, and you know what? 0.4 compared to 7 is actually rather large, and then we're going to square that. That's going to be a lot of uncertainty. I'm going to cheat and make this a significantly smaller number. Maybe you used some cameras that were on a timer to reduce your uncertainty in time. Okay, so absolute uncertainty in time is 0.1 seconds. Okay. What I'll do is first calculate the relative errors, or no, let's do it all at once. The relative uncertainty and the kinetic energy. I would sum up all the relative uncertainties. So that's delta M over M. We've got a delta D over D and a delta T over T. But remember, we have to weight each of these by their exponents. We've got an exponent of 2 for the measurements of D and T. So I'll put a 2 here, 2 here, then we square everything. Then we add, and then we take the squirt, the square root. That's what it means to add in quadrature. So you know what? I'll go ahead and use the 1/2 power notation here for the square root. Delta M over M, we've got an uncertainty of 2. Oops, forgot to square this one. Uncertainty of 2 compared to 130, square that. And then we've got an uncertainty of 0.5 for the distance compared to 100, square all that. 2 times an uncertainty of 0.1 compared to 7, square all that, and then we would multiply or raise to the 1/2 power. That's the 1/2 power, take the square root. So before I plug everything in, again, it's nice to see how each of these compares. 2 divided by 130 squared. And you see how small that number is? This says 2.4 basically times 10 to the negative fourth. I guess I'll go ahead and write that out. 0.00024. This is after I've already squared it, mind you. And if you're doing this in a computer, that can make things easier. All right, 2 times a half is 1. So this is 1/100th squared. I believe I did that right. Let's see, 1, 2, 3 zeros, 1, 2, 3 zeros. These are about the same actually. And lastly, 0.1 divided by 7 times 2, square that. And I get 0.0008. So surprisingly, I got lucky, and each of these is comparable in magnitude. So I would add them all up and then take the square root. 24 plus 0.0001. Take the square root, I get 0.03, which I can, that sounds suspicious. How can they all, I don't think I did that right. Oh, yes, because I'm taking the square root. Right, the square root of a small number is a number that's not so small, right? When you square a number less than 1, you get an even smaller number. So if you take the square root of a number less than 1, you should get a number that's not so small. So this is about 3% uncertain. Hope I did that right. That's a percent sign, 3%. So let's convert that back into an absolute uncertainty. First, I need to find the value of Q best. I would just plug my best estimates of mass, distance, and time into the formula for kinetic energy. My best estimate for the mass is the 130. The distance was the 100, and the time was 7. Sorry. Okay, 13,000, I'll round it to 270. Yeah. And the units there, well, we're going to talk about this later in the semester. They're joules. The SI unit of energy is not a calorie or a BTU, it's joule. Okay, so the absolute uncertainty in the kinetic energy, we just take 3%, which is the relative error, 3% of 13,270 joules. And I get, I'll round that to 400 joules. So the kinetic energy is likely, assuming our measurements were good and the estimation of the errors was reasonable, the value for the kinetic energy of this person on a bike is likely in this range, 13,270 plus or minus 400 joules. And we could rewrite that, of course. Okay, I'm going to be lame and do this in the calculator. 12,870 joules, I should really put the units there, is less than or equal to the kinetic energy is less than or equal to 13,670 joules. So that's the upper end of the range of likely values. This is the lower end. Once again, can we convince ourselves that this formula is legitimate? We could just go back to the formula and choose the numbers in such a way that we would get the likeliest high value and the likeliest low value. So let's do that right now. The maximum likely value of K. Well, in the numerator, we would want to put the largest value of D, the largest value of M, and in the denominator, we'll choose the smallest value for the time. And I think I'll just skip the part where I write everything down. So I'll go ahead and plug in 1/2 times the mass of, well, maybe I should write things down so you can follow the steps. Okay. The mass on the high end would be 132. And the distance on the high end would be 100 plus 0.5. The time on the low end would be 7 minus 1/10 of a second, so 6.9. So the highest likely value, and again, we're hoping for a number like this one to give us confidence that this formula works. 100.5 squared divided by 6.9 squared, 14,000. It's a little higher than this, but reasonably close agreement. The lowest likely value, well, this time I'll go with the lowest probable value of the mass, which would be 128. I'll go with the lowest probable distance, which is 99.5. And the highest time, let's make the denominator as large as possible. So that would be 7.1 seconds. And we're hoping that this minimum likely value using this method comes out similar to this one. 128 divided by 2 times 99.5 squared divided by 7.1 squared. 12,570 joules. Okay, 12,570 is fairly close to this, and 13,670 is fairly close to 14,000. So I'm happy with that agreement. Maybe at this point you're wondering, what's the point of using this more elaborate formula here? Because it looks kind of gnarly. Why not just every time use this method that I'm describing where you reason through whether you should plug in the highest or lowest value? And the reason is because this is systematic. This works for any product and quotient. You could program it into a calculator more easily, and we probably will be doing that later in the semester. And also, there are many formulas one would encounter in physical sciences where the formula that where it's not simply a product or a quotient. It could have a sign function in there, or some other non-integer power, or exponential functions, or a bunch of combinations of those. And it turns out that there's an even more general formula involving partial derivatives, and that formula includes this as a special case. So this is our first look at this one single formula that will allow you to calculate propagated error for a variety of circumstances. So hopefully you've seen how that works. You should get some practice with that. Maybe go back and rework one of these examples, because you will be doing this for at least 2, probably 3 of your lab reports.